Can alien worlds be even more suitable for life than our Earth? Would exoplanets with more extreme seasons, summer, fall, winter, spring, be more suitable or less suitable for life? How all this can help us in our quest to discover life around other planets? You'll find the answers in today's episode of my podcast, Astro Edge. Are you ready? Engage!
Welcome to Astro Edge, weekly broadcast presenting highlights of leading-edge research in astronomy and astrophysics.
Today's paper is Super Habitability of High Obliquity and High Eccentricity Planets. The first author is Jonathan Jernigan. He is an undergraduate student at Purdue University. The second author is Emily LaFlèche. She is a PhD student at the same university. This paper is about exoplanets, planets which orbit other stars. We've already discovered more than 5,000 of exoplanets. Before talking about super habitability, let's talk about habitability. What is a habitable exoplanet? Such a planet should be rocky, so it's like an Earth, not much larger than Earth, and it should be located close enough to its star to be able to maintain liquid water, oceans on its surface. Take Earth as an example. If you move it closer to the Sun, where Mercury is, it will get too hot because there is too much sunlight. So the oceans will evaporate and life as we know it won't be able to exist. If instead we move it further away, where Mars is, the oceans would freeze out and again life as we know it would not be able to exist. So there is a range of distances from the star for an exoplanet where liquid water, oceans can exist. What about super habitability? There might be exoplanets out there who are not just suitable for life, but in fact may be even more suitable to life than Earth. And that may result in more animals, more plants existing on that planet, or perhaps it would result in a wider variety of species. It happens that just being in the habitable zone, not too far, not too close to your own star, for water to exist in liquid form is not sufficient to describe how suitable the planet is for life. There are other important parameters of the planet. For example, obliquity. Obliquity is also called axial tilt. Planets spin around its axis. That's what creates sequence of days and nights. As you can see from this picture, the Earth axial tilt or obliquity is not very large. It's around 23 degrees. The spin axis of planets always points in the same direction, as you can see in this picture. As Earth or any other planet spins around its star, the spin direction is always pointing in the same point in the sky. For Earth, it's a polar star direction. The tilt angle is different for different planets in the solar system. It's 23 degrees for Earth, similar for Mars. It's almost 0 degrees for Jupiter. Because of this tilt, or obliquity, we get seasons. As you can see here, there are some positions in the orbit when Earth, specifically the northern hemisphere, gets more light, so we get summer in the northern hemisphere. On the opposite side of the orbit, we get less light, so we get winter in the northern hemisphere. The opposite is true for the southern hemisphere. So these are tilts of planets in the solar system. You can see the Earth tilt is 23 degrees, so it's moderate obliquity. Mars has a similar tilt. So both of these planets get similar seasonal changes. They get summers, they get winters. There are planets like Jupiter which have zero or almost zero obliquity. They basically get no seasonal changes. And there are planets like Uranus where it's almost on its side. The obliquity is 82 degrees. So the seasonal changes can become quite extreme. The reason the axis of the Earth and other planets spin is always pointing in the same direction in the sky is due to a physical law, conservation of angular momentum. The other important property of exoplanet is the eccentricity of their orbits. Eccentricity is basically how circular the orbit is of the planet orbiting its star. For Earth, the orbit is almost exactly circular. So Earth eccentricity is very small, it's close to zero. As the orbit gets more and more elongated, the eccentricity grows, and for the extreme case, it becomes 1. When it's 1, it's parabola, and the exoplanet basically flies away and never comes back. In the solar system, eccentricity of planetary orbits is pretty small. This is not the case for some of the exoplanets we are discovering. So the goal of this paper is to build a model of life on an exoplanet. Highly detailed and sophisticated model, which describes its atmosphere, its oceans, and also the life. And then the model explores different possibilities. It explores exoplanets with high obliquity or high tilt angle, all the way up to 90 degrees, largest possible obliquity. And also explores a range of eccentricities, all the way up to 0.4. This is highly elongated orbits. 0 corresponds to circular orbit. The researchers are using sophisticated models to describe processes on exoplanets. They have a three-dimensional atmospheric model, which describes things like winds, temperature changes, humidity, pressure changes, etc. Because it's three-dimensional, it can model or describe such complex things like cyclones, hurricanes, clouds. Also, model includes chemistry. They describe how the concentration of oxygen, methane, and other molecules change in the atmosphere. They also use a three-dimensional biology model, which describes things like photosynthesis, respiration, production of methane, and other things related to life. They also use three-dimensional ocean model, because the three-dimensional can describe things like ocean currents, heat, salinity, how much salt in the water, and life nutrients in the water. The model also talks about sea ice, percentage of ice coverage, ice thickness, wind forcing, ice drifting in ocean currents. So overall, this is a very sophisticated model. So what is a three-dimensional model and why it's better than other kinds of models? The simplest models scientists make, they're one-dimensional. There is only one dimension where something can change. For example, its height. You try to describe the atmosphere of Earth, and then you describe how things change with height. Let's say temperature, pressure, etc. The width and depth don't exist. It's basically assumed that all these quantities are the same if we move in left, right, or away from us or towards us. They may also be two-dimensional models. Let's say we describe the width and the height. But the most realistic models are three-dimensional. Our world, the world surrounding us, is three-dimensional. So to correctly describe most of things we see around us, we do need three-dimensional models, which include width, height, and depth. So why do scientists use one-dimensional models if three-dimensional models are the best, by far the best? It's all about expense. How difficult it is to model something, how much computing time it takes. Just to give you an idea, a typical two-dimensional model would take 1,000 times longer to compute than a typical one-dimensional model. A typical three-dimensional model would take 1,000,000 times longer to compute something than a one-dimensional model. So scientists do like to use one-dimensional models, at least initially, when they're trying to figure out what's going on. But at some point, we have to switch to two or even three-dimensional models to correctly describe things. There is a standing joke among astrophysicists called spherical cow. If you use simple one-dimensional model to describe a cow, how a cow would look like? Obviously, it's going to look like a ball, a sphere. That's why it's a spherical cow, which is obviously totally wrong. So complex things like cows, they need three-dimensional models to be properly described. And that's the case for this particular paper. Three-dimensional model is essential to describe correctly things happening on exoplanet surface, things which affect life, like winds, ocean currents, cyclones, clouds, ice drifting back and forth. All of these require three-dimensional, very expensive model. Amazingly, despite these models all being three-dimensional, the experiments computed here wasn't too expensive. One experiment requires only one CPU core and completes in 10 days. In total, they had to run 35 experiments. In models, we have what we call free parameters, things we want to explore. And in this particular model, the two free parameters are obliquity, which was allowed to vary between 0 degrees and 90 degrees. The second free parameter was eccentricity of the orbit, which was allowed to vary between 0 and 0.4. And different combinations of these two parameters resulted in requirement to run 35 different models. It is important to also understand limitations of models we use. This particular model assumed that other parameters of the planets were the same as the Earth. The day length, surface air pressure, the amount of oxygen in the atmosphere, they are all set to present-day Earth values. Also, they assume that the star is basically Sun. So this model cannot be directly applied to exoplanets orbiting, for example, red dwarfs. Red dwarfs have spectrum very different from Sun spectrum. So the researchers would need to run different models using red dwarf spectrum for those exoplanets. This figure from the paper is a summary of the main results. There are two axes. On the bottom, this is the obliquity axis or the tilt angle axis. Here are the planets which have zero tilt angle. Remember, Earth has angle 23 degrees, so Earth would be around here, and they explored planets up to 90 degrees obliquity. The vertical axis basically describes how suitable to life this planet is. The larger the number, the more suitable to life the planet is. The larger volume of animals and plants would exist or can be sustained, and perhaps a larger variety of species may be sustained on this planet. As you can see, there are a few different lines describing their models. They have different colors. Let's concentrate on yellow line. Yellow line corresponds to circular orbits, zero eccentricity, like Earth orbit. So Earth would be around here. It has zero eccentricity and the obliquity angle is 23 degrees. As you can see, if you take exoplanets with circular orbits and then you start increasing the tilt angle from zero, which means there are no seasons on that planet, you move up to where the Earth is, we do get seasons, and then you keep increasing obliquity. You see what's happening? The curve moves up, which means the larger the obliquity angle is, the more suitable to life the planet becomes. What is very new result in this paper and very interesting. Even if you go to very extreme obliquity, where the planet is basically laying on its side all the way to 90 degrees, the trend continues. The planet becomes more and more suitable to life. This is somewhat unexpected. One would naively think if you have extreme seasons on the planet, extreme changes from summer to winter, it's probably not good for life. This is not the case in this paper. Another trend you can see, as you increase eccentricity of the orbit, this means we are moving from yellow to orange to pink and so on, you also increase the planet's ability to support life. And here's what they're saying in the paper. Perhaps most surprising, the combination of high obliquity and high eccentricity supports marine biospheres that are more productive than present-day Earth in our model. This is not obvious result. Naively, you would think when you create more extreme seasons, things get harsher for life, not according to the model. Important point here is that they're focusing on marine life. They're not talking much about animals living on the surface. And they do point in the paper that perhaps for some of their models, the life for surface animals can become unbearable. Seasons might become too extreme for such life to exist in large quantities. But why is this the case? Why making more extreme seasons make the planet more suitable to life? The researchers have the explanation. From their analysis, when you increase seasonal changes, it breaks density stratification within ocean. And what is a stratification in an ocean? If their seasons are mild, in their models, things which are near the surface of the ocean stay there. Things which are deeper stay where they are, deeper. And in between, they stay there, in between. So there is not much mixing between different layers in the ocean. The ocean remains stratified. The researchers say that when seasons get extreme, this stratification breaks down and they see a lot of circulation. There is a lot of movement from the top layer of the ocean down to the bottom layer. And that allows nutrient-rich deep waters to mix with nutrient-depleted surface waters. And that stimulates photosynthetic activity, so creates more life. At the end, the scientists argue that planets with high tilt angle and or high eccentricity may be super habitable worlds that are particularly favorable for exoplanet life detection. One important point about this paper, they are talking about essentially Earth twins. We haven't discovered Earth twins yet. You can look up episode 1 of this series where I describe the chances to discover Earth twins in the near future using future telescopes. And the Earth twin is a planet which is similar to Earth in size, but also it orbits a star similar to Sun, and it orbits it at a similar distance. We haven't discovered Earth twins yet, but we will be discovering them soon. So this model paper will be very useful when we do discover such Earth twins in the near future. In conclusion, highly sophisticated model of exoplanet predicts that some exoplanets may not be just suitable to life to a similar degree as our planet Earth, but can be even more suitable to life than Earth. This is called superhabitability. What is interesting and kind of unusual, that planets with extreme seasons, with very large tilt angle, obliquity, or large eccentricity, or both, can be in fact better suitable to life than our planet Earth. This is a very important result, helping us a great deal in our quest to discover life around other planets. In my book, the research does have an edge. I'd really love to get a feedback from you, so please leave a comment down below. Also, please hit the like button and subscribe to this channel. See you next time.